Thank you. Okay, welcome back to our second task in the afternoon. And I'd like to introduce you to Christophe Haen from CERN, and he will tell us about monitoring at CERN.
So, hello everybody, thanks a lot for the introduction. So, as it was just said, I will speak today about how monitoring is addressed at CERN. But before starting, I would like to cover myself with a little disclaimer. First of all, what I will present now covers only really a small fraction of all the monitoring which is done at CERN. And this is really not intended to be a comparison of all the software, but rather an objective description, let's say. Also, I'm not an expert in all the solution I will present, but I will of course do my best to answer any of your questions. I will start by presenting a bit what CERN is and what CERN does. And then what we'll do is to go through different departments at CERN that have different type of environment and thus different monitoring solution. And finally, we'll have a look at some of our future plan. So I was explained that some among you are real monitoring experts in the meaning that they really develop tools. And some others are beginners that want to introduce themselves into the monitoring world. I think this talk can be relevant for both audiences. On one hand, it can give some ideas of feature that the experts might want to include into their software. And for the beginners, I think it's anyway always good to see what the others are doing. So if I take now a random person and ask him what CERN is, there is a good chance that this person has only read or seen the movie Angel and Demon and will tell me that CERN is the place where we have the glass cathedral. This is not true, we don't have a glass cathedral, and the visitors are always disappointed by this. Now, most of the people will tell you that CERN is the place where all the crazy physicists. Now, this is true. We have some physicists that are completely bananas. And now, naturally, crazy physicists leads to huge machines that will destroy the world. We don't have big machines, but we'll destroy the world. Or it's the opposite, I never remember what I should say. No, what CERN really is the European Organization for Nuclear Research. You can trust me, this is what CERN stands for. Historically, it was founded after the war so that Europe keeps a dominant position in high energy physics research. So the role of CERN is actually to provide all the infrastructure which is needed for this high energy physics research and to share the data with the community. If you read a bit on the internet or even the official communication, you will see a lot of those washing power terms, you know, like most respected center, biggest laboratory, largest facility, a place where there is the least girl in the world. It's really a place which is full of superlative, but one has to say that it's true that CERN is a big laboratory. This is a map which is probably even not up to date anymore, which shows you all the members of the collaboration. So even if there is European in the title, you see that it's more than this. So CERN has many projects running. You might, for example, have heard of those neutrinos faster than light. But the main project is certainly the LHC. So LHC stands for Large Hadron Collider. It's a huge ring, 27 kilometers circumference, 100 meters below the ground, in which you accelerate trains of particles in both directions. This machine is by far the most complex machine ever built by the human being. It's the coldest place of the universe. It's the emptiest place of the universe. It accelerates particles at more than 99.9% of the speed of light. And it's really an amazing machine. Every day I learn more about it, and every day I'm more surprised that it can even start. It's really fantastic. So this machine is supposed to help us to understand how the universe works. And so that you get a bit an idea of this size for this nice physicist toy, here is a picture that was taken during a ski trip. So here is standing on the Mont Jura. In the bottom you have the Alps with the Mont Blanc, or the Geneva region, with the lake. In blue is the LHC. This is the SPS, another accelerator, yet another one, my house. So it's really a big machine. After accelerating those particles, what you do is to put them into collision, and you do this at 4 different interaction points. And on top of those interaction points, you place detectors. So a detector is like a big camera which will take snapshot of what is happening when 2 particles collide. There are 4 main experiments. The first one is ALICE. So ALICE is looking at kind of a soup that was there right after the Big Bang. So on the bottom left, well, the color is not fantastic, but on the bottom left, you can see a sketcher of the detector. So you see that when I'm speaking about a camera, it's a big camera, because here you have the two characters. So here I have the dimension. And this, I don't know if you can clearly see it, but it's an example of a picture which is taken by this detector. And the whole game is that out of this mess, you say what is going on. The second experiment is ATLAS. So ATLAS is one of the famous and general purpose detector. So it's looking at many different things, among which the famous Higgs boson. ATLAS is really a giant detector. You can see this on the sketcher on the left. The size of ATLAS is half the size of the Cathedral Notre-Dame de Paris. So it's really a monster. CMS is the second famous and general purpose detector. It's looking at exactly the same things than ATLAS, but using different technical solutions. Finally, we're left with the fourth one, which is LHCb, which is the experiment for which I'm working for. So LHCb is the smallest of all four experiments, but is also the most precise. What LHCb is doing is trying to understand the origin of the difference between matter and antimatter. And for the anecdote, we are doing this by looking at particles that are called beauty and charm. So just this makes it the best experiment of all four. So now we have taken our pictures. We need to analyze them. And this is done on the grid. So the grid consists in putting together all the computer resources of all the members of the collaboration. The reason for doing this is that the amount of data which is produced by the experiment is huge. It's at least 25 petabytes of data a year. So you really need big infrastructure to analyze this. So if you want to summarize all of this, you have the LHC, which is producing the data. The experiments are recording them. You analyze them on the grid, and CERN is running the show. And all those different steps are relying on large IT infrastructure. And this is why we need the monitoring. So what we'll be doing now is to have a look at some groups that are taking care of those different steps, have a look at their environment and their specificities, and see what monitoring strategy they decided to have. And we'll start with the accelerators control group. So this group is in charge of taking care of controlling the proper behavior of all the accelerators. There is not only one accelerator. LHC is one, but there is a whole chain of them. And this group is responsible for all of them. You can see here that I wrote that the infrastructure covers a large geographical distance. It's typically in the order of 30 to 40 kilometers, which can seem small at the scale of internet. But here, we're speaking about machine where every 25 nanoseconds something is happening. So here you're speaking real time. And when you're speaking real time, 30 kilometers is a large distance. Yeah. So they have a very heterogeneous environment. They are running quite a few standard servers, but they also have much more exotic hardwares, like PLC, like fan tray, VME, FPGAs, many exotic things. And they're running mostly Linux, including the real-time operating system. So in order to monitor all this, they have developed a tool which is called Diamond. The reason for developing Diamond was to provide to all the operator of the accelerators with an easy view of the monitoring status of the accelerators. But there were two requirements. First of all, the footprint on the client must be extremely low, not to perturbate all the real-time operation. Also, since there are many different types of operator for an accelerator, you needed an interface that you can easily customize. So they have developed Diamond. Diamond has evolved, has merged with some other solution from similar groups that had similar needs, and in the end, it gave birth quite recently to a solution which is called C2MON. So C2MON addresses all the requirements of Diamond, but adds two more, which is to use only open source technologies and proven technologies. So in a minute, I will explain you how C2MON works, but I first listed here some of the technologies that are used. You can see that there is quite a lot of Java with the Spring framework, with the JMS middleware, or the iBatis library. Note that this group is using Oracle as a database backend, but you might as well use any other database backend. It's completely compatible. And they're using eCache and Terracotta for the different cache layers. So C2MON works in a 3 layers architecture, and those layers are communicating with the messaging system. The data flow goes from bottom to up. So completely in the bottom, you have the DAC part, which really gathers the data. Then you have the core part, which treats them, and finally you present them. C2MON has been developed with 3 constraints in mind. The first one is that it should be modular. The second is that it should be highly available. And finally, it should be able to perform intensive monitoring. And we'll see this through the different layers. The first one is the DAC, which stands for data acquisition. So it's really supposed to gather the data. It can either act as a poller, either passively receives the data. The principle of a DAC is that for one type of check, you will have one single dedicated DAC instance running for all your equipment. So for example, all SNMP-based check will go through a dedicated DAC instance. This approach is quite interesting because this allows you to add a new measure with an existing DAC without perturbating the monitoring system at all. You can basically add a new check without stopping the production system, which is nice for the high availability constraint. The high availability constraint even goes further than this in this layer, because if you make a software update, every DAC knows whether it's able to apply the changes while running or not. If it is, fine, it will do it. Otherwise, you obviously have a bit more control on what is happening. It's also at this layer that happen all the filtering and smoothing capabilities, so that you don't fill in the database with useless information. So now you go to the core part. So first of all, the core part comes with a plugin system. So if you're ever missing a functionality, you can always add it thanks to this. The core has been designed to run in a cluster setup. The way this works is that all the servers that belong to the cluster are sharing a common cache. And from this cluster, you can add or remove a server on the fly. If you want to make a server upgrade, take it out from the pool, upgrade it, put it back. No service interruption at all. Once again, it's very nice for the high availability constraint. Finally, the fact that you can extend this core part, this central part, as much as you want with this system, plus the fact that all your DAC instances can be spread wherever on your environment, finally added to the fact that the database backend is cached, makes this solution an extremely scalable solution. This group is having, if I remember properly, 80,000 checks running every 20 or 30 seconds. And they are far from throttling. I mean, there is still a lot of room for it. So it really scales really well. We are now left with the client presentation. So because we wanted a very modular architecture, the easiest was to develop a common API. And this is what was done. So C2MON comes with already quite a few views provided. You have, for example, a video stream or a web interface. But there is one that I personally find really cool, which is the replay functionality. So you give it a start date, you give it an end date, and this will replay for you all the sequence of events that happen, which is really convenient if you have to diagnose cascade failure, for example. So this is really nice functionality. So this is how the accelerator addressed the monitoring. Now let's have a look at the experiments. But first of all, I would like to explain why the experiment needs such a large IT environment. The LHC has a crossing rate of 40 megahertz, and this means that every second you have between 600 million and 1 billionth events happening, an event being a collision between two particles. The data that represents one event runs from a few kilobytes to a few megabytes, and I personally don't know any computer facility which is able to transport and to store a few megabytes 600 million times a second. So that's what you need to do is to filter the event. And that's where the big computer environment kicks in. So, yeah. So that's what the bigger part of the environment is called a filtering farm. We'll start with LHCb. I know that it's not the alphabetical order, but it's the one that I know the best. So LHCb has roughly 2,000 servers, 200 switches, and 400 embedded processors. We are running mostly Linux, but we also have a few Windows machines that we have to care about. I would like to come back first a bit on this farm principle. What you need to filter the event is CPU, it's memory, but you don't need storage. And this is why the farm is running diskless. So for 30 nodes that are running diskless, you have one machine, which is called a controller, that will provide to those nodes with the file system and so on. And this group, 30 nodes plus one controller, is called a subfarm. LHCb is running 60 subfarm. So except of running diskless, our environment is standard. It's fairly big, but it's standard. And this is why we can use standard tool. And the tool we are using is Ichinga with Modgerman. Before using Ichinga, we were using Nagios, a single instance, and it was simply not coping with the load anymore. We needed to replace it. And there were two main reasons to go for Ichinga. The first one was that the configuration files were compatible. In the end, we completely rewrote them, but at the time, it seemed to be a good reason for it. The second one is that the support provided by the community is really great. So if you guys are a member of this community, thanks a lot. As I said, we are using Mod-Gearman to distribute the work. And we are having 60 Mod-Gearman workers. If you remember, this is the same number as the amount of subfarm. And it's not a coincidence. What we are having is 1 Gearman worker per controller. But there is no special queue whatsoever. All the controllers get randomly assigned check to execute anywhere on the environment. And this setup really works like a charm. We are able to perform 45,000 checks without any latency whatsoever. So we're really happy with this setup. In order to execute the check on Linux, we are using NRP, NSClient++ for what concerns Windows, which by the way is very convenient because it offers the same interface than NRP. And we have a few SNMP check for what? For the switches and for the disk pools. Now for the check themselves, we are using almost only standard tools. We really had to write very few custom checks that was really for very particular purposes, probably out of the mind of a physicist or something like this. So, as I said, it's almost a system which is out of the box, and only a very few tweaks in the configuration, but the rest runs very happily. Let's have a look at what Atlas is doing. So Atlas has 3,000 hosts, but it has a similar environment as LHCb with all this diskless subfarm. What I will say now concerns only the system monitoring. No switches, no front end. What Atlas is having is 80 independent Nagios instances, 1 per controller. And they are all feeding a central MySQL cluster and an ARD storage. What Atlas had to do was to develop a custom web interface in order to be able to see the overview status coming from all the instances. 1 year of database is 8.5 gigabytes, but 1 year ARD is 18 gigabytes. The reason that ARD files are so much bigger is because they have a very tiny granularity. They're using only custom checks based on NRP, IPMI, and SNMP. Now this setup works well since 2008, I think, but it's too much administration. That's why they want to move out. They have 2 requirements though. The first one is also to keep some configuration compatibility, and that's another one which is much stronger is that the new tool, the philosophy of the new tool, should somehow be compatible with ConfDB. So ConfDB is a custom tool that Atlas developed, which is kind of an inventory database out of which the monitoring configuration is generated. So providing those requirements, plus the fact that they're benefiting from our experience, it's very likely that they go extremely soon for production with Ichinga and Mod-Gearman in a similar setup than we are. Note that this group also uses Ganglia as a performance monitoring on a few hundred hosts, but I will speak about Ganglia a bit later. CMS now. So CMS is also running 3,000 hosts, but they don't have diskless farm. All their servers are standard. So what they have is actually the same tools than we have, but they're using it a different way, and it performs as good. They are having 1 server which is dedicated to all the PNP business, 1 server which is running Ichinga, and 1 machine which is running the single Gearman worker. The way they manage to achieve 90,000 checks every 2 minutes, thanks to this setup, is because they're using check multi plugin. So this plugin, for those that don't know, allow you to execute several remote check with a single NRP call and reduces really a lot the overhead of it. So their setup works well and they're happy with this. Now something that they told me to tell you guys from the Ichinga community is that they're really happy about the JSON output of the interface, because then they can feed their custom script with it easily. So they're happy with this. Now we are left with Alice. So because of the way the Alice experiment is working, they happen to have several groups taking care of portion of their environment. And the one we'll be looking at is called the Alice HLT. So their environment is fairly small. It's only 220 servers, 63 switches, but they have FPGAs and they have GPUs, which is that they want to monitor, of course. So for this, they're also using two tools. They're using Ganglia as a performance monitoring, and they're using CSMIS, which is a homemade system for all the other matters. We'll start with Ganglia. As I said, Ganglia is a performance monitoring system. That means that it doesn't have any notification capabilities by itself. Ganglia is really meant to provide you with nice aggregated graph based on RRD tool that you can then see through some web interface. The way Ganglia works is that you will define cluster of machine by monitoring interest, let's say. And then those cluster of machine will push upwards the information in a tree-like structure. So first of all, having such a tree-like structure really distributes the loads because all the smoothing is done at the different layers. So it scales really well. Now there is another interesting feature in Ganglia is that within a cluster, you can address those connection points to the graph either via unicast, either via multicast. And this means that you have a very redundant setup almost for free. You hardly have any blackout in your graph, which is always so annoying to have. On the right, you have an example of interface that you can have with Ganglia. And the very latest version of Ganglia actually provides you with a feature. You can compare host based on regular expression. So this is really a powerful tool if you want to compare different performances. Now, one reason that brought Alice to use this was that NVIDIA was providing them with the Ganglia probes for the GPUs. So this is really a strong call for it. The second tool that they're using is CSMIS. So CSMIS is a homemade tool in collaboration with some universities, mainly German, if I remember properly. CSMIS is more than just a monitoring system. It's entered this autonomous software range. So CSMIS comes with an inventory module, a monitoring core, and all a set of rule-based system. The way this works is that the user will fill in the inventory module with information about the environment, out of which they will generate the monitoring configuration. The user will also define some rules that will be evaluated against every event and action to be taken. So CSMIS works in a distributed manner. First of all, vertically, because for one client, you will have one management framework. Now it also can work in a horizontal manner. If, for example, the server which is running the management framework suffers too much from the load, you can start a second instance of the management framework, and those frameworks will start exchanging messages that are actually tasks, so they will literally share the work between them, and you can add as many framework and so on as you want. The load will be equally shared. So it's quite a powerful system. They're using it for monitoring their servers, their switches also. They have some rules that try to restart servers, things like this, but they also use it to get some emails. So they're using it in production for a while and are very happy with this. The only maybe weak point that they would complain a bit about is about the way the information is then presented through the web interface. And this is why what they're considering to do now is to feed Ganglia with the output of CSMIS. So we are now done with the monitoring of the experiments. Now we have filtered our data, we need to analyze them. And this is done, as I said, on the grid. The grid is primarily operated by the CERN IT department. But this department has another role, which is to take care of the IT center. So the IT center is the basic infrastructure, which is used by every people at CERN. So it's the email, it's the database, it's the web, it's all really the core infrastructure. The environment is also fairly heterogeneous. They have several Linuxes, they have some Windows, they have some Macs even. In total, it's more than 9,000 servers and 2,600 switches. So it's really a big center. It represents more than 3.5 megawatt facility. It's a lot. Here you have part of the IT center. And for your information, here on the yellow rack sits some of the main core internet router. So all of you here should hope that this never burns down. So now I'll tell you how the IT department addresses the Linux monitoring. At the time when this center was designed more than 10 years ago, it was really a center at the bleeding edge, as much in terms of performance than in terms of amount of machine. And they had no other choice than developing their own tools. And this is why for the Linux monitoring, they have developed something which is called the Lemon. So Lemon is actually part of a whole set of tools that were developed primarily at CERN in collaboration of the European Union and all this political stuff, which were designed to address all the large fabric management. So Lemon works in a server-client way. So this means that every client is running an agent, and then the information are populated to a central server. So Lemon come also with notification capabilities and rule-based evaluation. And we'll start to have a look at the agent. Every node that you will monitor will be running a so-called monitoring agent. The role of the monitoring agent is only to start one or several sensors. A sensor will be like a toolbox for monitoring. So for example, you have the Linux sensor. Now those sensors implement metric classes. Class in the same meaning than the object-oriented programming. So one metric class of the Linux sensor will be the CPU load. And then the sensor starts metric instances. So it's simply a given measure with a given configuration. This philosophy allows you to reuse the same piece of code for many different configurations. Now this is really the basic principle of the monitoring agent, and it comes with a lot of agents already. And there is one which is a bit particular, which is called the exception sensor. So this sensor actually reacts at the output of the other sensors. So it's, for example, there that sits all the rule-based evaluation. Now, for all the matter which concern the monitoring of a particular node, everything is local to the node. The configuration, the scheduling of the check, the evaluation of the rules, the recovery attempt, everything is done locally and stored on a local cache. There is absolutely no interaction so far with the central server. Of course, it would be nice if you could somehow gather the data together, and this is what is done. So all the nodes will then send the information to a central repository. What the central repository does is, first of all, to fill in the database, which keeps the history for 1 year, and RD files. And what you can then do is browse those data with a very nice web interface, which provides really accurate and useful information of your whole environment. But you can also browse this with command line interface, which you can, by the way, use also to directly query the local cache on the machine. Now, something which is also interesting is the way the node sends the information to the central repository. What you normally give to your nodes is a list of servers, but those servers are not running in a cluster setup. They are complete independent instances of servers, even with their own database. The interest of doing this is, for example, if you want to aggregate the data in a different way, or it also provides some redundancy. If one of the servers fails, you just go on the other one. Finally, imagine if you have a development version of the server to test. You can have it running in parallel of the production server with the current and running data without putting in dangerous setup at all. So it's quite a convenient way of doing. Here on the left, you have an example of this web interface which is provided. This is based on Django. I think it's quite a new version of the web interface. Now, the fact that all the smartness that concerns the monitoring is put on the local node makes this solution an extremely scalable solution. The IT center is having 1.7 million different data sources, and it's not throttling at all. It's far from the top, really. It's really performing really well. 1 year of data in the database is 6 terabytes, and 8 years of RD files is only 45 gigabytes. So this is a solution that performs well for extremely large environment. So now back to our data flow. We need to analyze the picture we've taken before, and this is done on the grid. I explained before that the grid consists in putting together the resources of all the members of the collaboration. In total, it represents 35 countries spread all over the world, and it's 170 different sites. So this means 170 different environments, 170 different admin team, 170 different tools, 170 different what you want. I think this environment is as heterogeneous as it can be. So when they have developed all this grid principle and philosophy and so on, they have developed many tools that were supposed to fit this philosophy that was really innovative at the time. The cloud was not existing. So they have developed tools which are meant to control the grid, some for deploying it, and of course one for the monitoring. So the software which is made for monitoring is called SAM. So SAM is actually an aggregation of open source blocks that are then shipped together or arranged in such a way that there then fits to the worldwide monitoring, but also fits well with all the different blocks that were developed for the grid. So for this reason, because it fits with the other tools, SAM comes with a very advanced notification and reporting system. You can have very advanced ticket opening, and it's really quite convenient for this. And at the end of the chain, you are presented with the data on a web interface or on a REST API in still a philosophy that match in a manner that match the philosophy of the grid. That means that the user should have no idea where his things are running and so on. So SAM works in a distributed manner. This means that there is one central instance at CERN that knows everything about the grid, and then there are local instances that obviously know only what is local. So you have one local instance per country and one local instance per what is called a virtual organization. So a virtual organization consists simply in grouping sites by point of interest rather than geographical concerns. As I said, SAM is an aggregation of many components. You have, first of all, 3 databases. One contains the topology of your environment, one contains information about what you actually want to monitor, and finally you have one for the results. Now I said that CERN knows everything. This is not true. CERN does not want to know everything. It doesn't care about the low-level detail of the grid. What CERN wants is to have general status, know how things are globally performing. On the other hand, the local sites, they want to know how their servers are going on. And this is why every local site can define much more information in their database that will simply not be forwarded at CERN. All the local instances are communicating with CERN with the messaging system, which is ActiveMQ. And by the way, it's also this media which is used to communicate very often with the other component of the grid. Now, finally, we need to have the monitoring core itself, and this is based on Nagios. The reason for using Nagios in this block, so started already quite a while ago, was that a survey was done with all those administrators of those 170 different sites, and they were asked with what software they feel the more comfortable, and it was with Nagios. So it's really, once again, a testimony that Nagios was really worldwide appreciated. There are more blocks than this, but are not really relevant. Some blocks are, for example, computing some metrics which are relevant for the grid. Now, what we have in the end is 45 Nagios instances that are feeding the local databases and that are feeding CERN. CERN receives every day 800,000 records, and they keep the history for 6 months, so which represents 800 gigabytes. At the end, you get the data presented in a way which is suitable for the grid. Here you have an example. This is called the grid map. So every big square represents a country or virtual organization, and every square inside represents the status of one site. So you can immediately know where things are going wrong. This, for example, is China. So we've now done with our data stream. We have seen how the monitoring is done currently. It's time to look at some of our future plan. CERN is now entering a period which is a bit particular, which is called LS1, which stands for Long Shutdown 1. For 2 years, the LHC will be turned off, and it will be the opportunity to consolidate and improve the accelerator, but also the experiments and the IT center. The IT center needs to grow. By 2015, we plan to have 15,000 servers and 300,000 virtual machines. Now, there will not be more people than now to take care of all this. And we are conscious that having a lot of custom tools is a lot of maintenance. 10 years ago, it really made sense to develop those tools because they were not existing simply. But now, compared to giants like Google or Facebook, we are not so big anymore, and the tools exist now. It was not so long ago that Google came to visit CERN to see how we were doing. Now it's time to do the opposite. And this is why the IT department started what is called the Agile project, which consists in retiring some, not all, of our custom tools to join the community and participate to the community. This is an important point. So, for example, they will retire their custom fabric management system, which is called Quator, to use Puppet. Now, this also concerns the monitoring part. They have realized that for just the monitoring of the IT center, they have more than 30 different monitoring applications. In total, it's more than 40,000 producers that output 200 gigabytes of monitoring data per day. It's enormous, so you could think that you know everything about your center. This is not true, and the reason is that we are not using properly those data. What would be really convenient would be to say, for example, I realize that when the temperature in the room is 2 degrees higher, I perform 10% less well. This is what you want to say. And this is what the IT department will try to put in production with a new architecture. This architecture will be based only on open source and existing software with developing the least possible code. So this architecture will have 4 layers. In the bottom, you have the producers that output those data. So it's, for example, Lemon. You then need to aggregate those data. For the time being, they're considering and testing Apollo, which is a messaging system. It's, if I'm not mistaken, the successor of ActiveMQ. You then need to process the data. For this, they're evaluating HBase, which is part of the Hadoop framework. And finally, you can present those data. This setup should really allow us to have the high-level information as I described before. The only very single piece of code that they developed so far is here. It's an API so that the producer are completely agnostic to the technologies which is used at higher level. So this is currently being tested on only a few producers, not the 40,000, but they are quite sure that by 2015 this will be fully in production. So this idea of aggregating the results, making correlation of them, using them properly, and having higher level information is really an idea which is spread in all the departments at CERN. Now there is another approach, which is how much smartness you put into your monitoring. And for this, I would like to mention the initiative of Atlas. So Atlas is using a software which is called ESPER, which is an open source solution from ESPERTech. What ESPER is a complex event processing engine. What you do is to feed it with many different data sources. The origin of the data and the type of data doesn't matter as long as a certain format is respected. So they are feeding it with all the Netways instances, they are feeding it with the control system of the experiment, with really a lot of different data sources. And then what ESPER does is to try to match rules defined by the user. What is interesting is that those rules are not only concerning the events themselves between each other, but it can also make time-based correlation. And this is really a very powerful tool. The way Atlas is using it is that when a rule is matched, there will simply pop up a message on the screen of the operators telling, we think this problem is going on, you should call that person. There is no direct action which is taken at all. They're too scared for this. Now there is a little problem. To define those rules, you're using an SQL-like language. I personally don't know it, but I was told that this language is quite a hassle to learn. The way Atlas addressed this problem is that they have now 1 or maybe even 2 experts that are really specialists of this language and are now working with all the different groups to lie on the paper those rules. So this setup is now in production for a few months. It performs really well. It scales really well. They're really happy with this, and they really want to keep feeding it with more and more data and write more and more rules. Now, there is one final initiative that I would like to mention, which is what we are doing at LHCb and which is my research project. First of all, keep in mind that this is still highly experimental, but I think it's worth speaking about it. All those rule-based systems are really nice. They're performing really well. You can have thousands of rules. It all works fine. Now, the problem is that you still need an expert to write down those rules for you. And it can be quite complicated, as we have seen with ESPER. Also, if you start to have many different rules, maintaining it is extremely tedious, if not impossible. And this is the experience that shows it. What LHCb is trying to do is to have a different approach. First of all, we don't want to be as generic as those rule engine systems. We want to focus on a particular matter. And what we have chosen was the Linux system. No network, no Windows, only Linux. And what we want to provide is diagnostic and recovery solution with the least work possible for the system administrator. And to achieve this, the only way is that those rules that the expert would normally define, the software automatically discovers them. To reach this point, we are using two approaches. The first one is reinforcement learning. This means that with time and experience, the software will improve its diagnostic. And the second approach, which is quite original, is the experience sharing. If you, as a system administrator, are able to take care of, let's say, a web server, there are good chances that you are able to transpose your knowledge on another web server and diagnose and solve problems on this web server. This is quite intuitive for us, and this is exactly what we want to implement in our software. Now, it turns out that the object model represents this fairly well. You could, for example, say that a website is an aggregation of some data file, some configuration file, and an HTTPD daemon. Now, the very only thing that the administrator will have to say is, here, site 1 is a website, those are my data file, those are my configuration file, same for site 2, and this is it. From just this, we should be able to provide recovery, diagnostics. Now, presenting things in such a way has two advantages. First of all, it reduces quite a lot the description workload for the expert, as we have seen. Now, it has another consequence, which is even more interesting, is that sharing the experience in such a way really improves a lot the learning speed of our algorithm. On the right, you have a comparison between two curves that was obtained on a test bench. So we're having different websites running, and we randomly created problem on them. The blue curve shows how fast our software was learning when the experience was not shared, and the orange one is when the experience was shared. And you can see that the orange curve reaches the optimal value much faster. So once again, this is still very experimental and under heavy development, but the test we have done on some test benches on some...
Just one question, what are the numbers then for...
Okay, so this so this was the amount of replication, and these are the number of success, but it's because I would have to explain all the test bench, but it's because of the amount of errors that were randomly assigned and so on. So this, theoretically, you cannot reach higher than this point. So yeah, this is still highly experimental, but the results we have obtained at some test bench and on some real case, fairly small for the time being, are really encouraging. So now we are just about to develop it on, to deploy it on a much larger scale. And what we want to do is to really consolidate our algorithms first, to then release it to the whole community, hoping that there will be some help from the other experiments, and why not from you guys. So now we have seen many different softwares. We have seen some that are adapted if you have to make very intense and highly available monitoring, some standard solutions, some performance monitoring, some tools that were adapted for extremely large environment, some for monitoring across the globe. But still, this represents only a very small fraction of all the monitoring which is done at CERN. And many different aspects of the monitoring were actually not addressed, like, for example, how do you manage your configuration, how do you deploy it? Now, by preparing this presentation, I got to talk with many experts of different groups at CERN. And there are some points on which we all pretty much agree. First of all is that you cannot do everything with a single tool. The work, the efforts you will put into maintaining several tools doing exactly what you want is much less than the efforts you will have to put for forcing one software to reach your goals. So we shouldn't be scared of using several tools. But for this, we need to aggregate the tools and also aggregate the results if you then want to use them properly and reach this higher view that I mentioned before. What normally happens now is that if there is a problem going on, you will receive an SMS, you will receive an email. So normally you go, you fix the problem. Hopefully you try to understand what happens. And then you delete the SMS, you delete the email. That's it. This is not how it should be. Otherwise, those terabytes of database and logs that we have are completely wasted. All the departments consider now more and more smartness in the software. Not too much, but at least some. We all have now some powerful core solution that provides and fills our screen with thousands of buttons that are either red or green. Now, if you have a circuit breaker that jump, will have half of your screen completely red, and you will get thousands of email, whereas what you should get is one single email telling this particular circuit breaker is dead, and this is why your screen looks like the Italy flag now. Finally, there is one point that I think is pretty much useless to say it here, but we should really participate to the community. CERN has a long history of developing its own tool, and there was good reason for this. And actually, those tools are good. I'm not afraid of saying it, they were good. But the advertisement was really lame, so now it's time to catch up with the community and participate to it. And generally speaking, if we're missing a functionality in a given software, it's very likely that someone else is also missing it. So instead of having hundreds of people hacking the tool in their own corner, we should contact the community, participate, try to develop it with this. It will be much more stable, much more robust, we'll have much more help, and it will be much less work for you. So it's really a win-win situation. And I know that some among you are really very active members of this community. So to those guys, I really want to say a big thank you, because we are benefiting from your work. So thanks a lot. Now my presentation is over, and I will be happy to answer any of your questions if there is, and if I can.
Thank you.
Welcome.
Hello? Okay. Any questions?
Very clear.
Okay. No one? Ah, I love you.
I don't.
So you're telling you want to participate in a community. How exactly this will happen? Will you make some kind of portal? Will you go on the standard Nagios forum portal, or?
So this has already started, first of all, especially with Puppet, because this was the first consideration that we decided we'd need, the CERN IT department at least, needed to retire their system because of changing the operating system very soon. There was some incompatibility, so they decided now is the time to go for Puppet. And not to reproduce some mistakes that were done in the past, they said immediately, we go with the community. So they contacted Puppet, and they have now really some people that are core developer in Puppet that are really actively exchanging. They are going for all the conferences or so on, so they really get involved in it. So there are good chances that if we keep using itching and things like this, the management at CERN will be much more kind to let people work also on the community during the working hours and things like this. So we can hope this. It seems to be the direction in which it's going. But yes, CERN's really now want to join the community actively, not only report bugs or things like this, but really have an active role there.
Someone else to be loved? No? Okay.
In one slide you showed that you have a lot of informations in the database, and beside that you have a lot of informations in RRD database. What is the reason for that? Cannot create the RRD files on the fly out of the database information?
For which either you're speaking about Atlas, either you're speaking about Lemon.
Oh, too much information for me to keep that all in my mind, sorry.
That's what I feared. Was it this one?
Yeah.
The reason is that the information are arranged in a different way. In the database, they are sorted by check, let's say, whereas the RRD files are per host basis. So they seemed to feel it more comfortable to do it at the software level. So that's how it's done.
So it's not able to have an additional table to get all that together in the database?
Oh yeah, it's definitely able to do so. And the schema of the database is extremely flexible because it even creates a table at runtime and things like this. So, but I personally cannot tell you in detail, but they seem that if you want now, if you're really interested, I can give you the contact for the person for this. But
it's, okay.
It's really done at the software level.
Only interested on the reason why. Yeah. Okay,
I don't
doesn't
know.
matter. Thanks.
Thank you.
Welcome.